Ladies and gentlemen, welcome to my online lecture. My name is Wancheng Zhu from Northeastern University, China. My topic is predicting the mining-induced disasters using cloud platform. About me. I got my PhD degree in mining engineering at Northeastern University, China in 2001, and I was promoted to full professor in 2006. Since year 2000, I worked in Hong Kong, Australia and Germany for more than 4 years, and gave lectures and presentations at many universities throughout Australia, Germany, Korea, Switzerland, UK and South Africa. In 2013, I was granted the China Youth Science and Technology Award. In 2015, Ian was entitled as Chongjiang Chair Professor by Ministry of Education of China, and was supported by the National Science Foundation for Distinguished Young Scholars of China. I am an active member of International Society of Rock Mechanics, ISRM, and the executive member of Chinese Society of Rock Mechanics and Engineering, CSRME. I am also an associate editor of International Journal of Rock Mechanics and Mining Sciences published by Elsevier, and member of editorial committee of Chinese Journal of Rock Mechanics and Engineering. This is outlined. The first is background and general idea. This slide shows the challenges for mining safety. China is rich in mineral resources. However, most of them are under severe mining conditions, especially for those who will be mined at depth over 1 kilometer in future. The mining experiences high risk of disasters such as rock burst, water outburst, and coal and gas outburst. Mine disaster is deadly tragedy. The diagram on the left simulates the serious damage of roadway and equipment caused by rock burst during mining operation. The middle figure shows the serious flooding accident in Gongchangling coal mine, Shanxi Province, China on March 28, 2010, which killed 38 people. The reason for the accident is that the coal mining face is connected with the Gulf water at right. Gas explosion at Jinsanga coal mine, Chongqing City, China, on October 31, 2016. Killed 33 persons. There is a national R&D project for mine safety undertaken by our research group. This project is to study the mechanism and prevention and ground control technology for major disasters in metal and non-metal mines. I designed this tea kettle model to show the frame of the project. In this project, there are 8 tasks. The first task is integrity theory of safe mining. The second is for slope instability at open pit. The third is for cavity failure at open pit. The fourth is for cavity failure at underground mine. The fifth task is about rock burst at deep mine. The sixth task is about surface subsidence induced by large-scale mining. The seventh task is monitoring and early warning of mine disasters and cloud platform. And the eighth is for emergency rescue and personnel protection. My work is on Task 7, focusing on disaster mechanism and precursory information, and cloud platform for monitoring and early warning, when the mechanism and prevention and control technology of mine disasters become available. The related technologies will be put into practice at typical mines, This slide shows the general idea of the cloud platform for early warning of mine disasters. I imaged cloud platform as a cloud Superman, which has performance of ultra-high computing and huge storage capacity. The body of cloud Superman is offered by Alibaba, Huawei and other cloud service providers. The brain is provided by us, which is focus of our study. It contains disaster-causing mechanism, early warning methods, early warning indices, early warning thresholds. They are the theoretical and technical basis for prediction and early warning of mine disasters. Two legs of Superman are test data, theoretical models and in-field monitoring data. Two hands of Superman are to propose EW method based on the combination of monitoring data and numerical simulation. Finally, early warning and alarm information are released with multiple terminals to mines. This slide shows the cloud platform for early warning of mine disaster based on Internet of Things, cloud computing and virtual reality technology. We collected so many data from data with different sensors. It is called monitoring with Internet of Things. In this regard, the data of equipment state, deformation and displacement of rock, microseismic monitoring data, mine environment and position and state of personnel are collected and uploaded to cloud platform. On the other hand, we got the rock mass information and established the numerical model of mine. The numerical results are also uploaded to cloud platform. At the cloud platform, the monitoring data and numerical data are integrated and used to predict or early warn the mine disasters. The results are output to VR system, where the disasters such as slope instability, cavity instability and roof falling should be evaluated and predicted. Research content of the project lies in three aspects. The first is rock failure mechanism and precursory feature associated with mining-induced disasters. The second is in situ monitoring and numerical simulation for mining-induced disasters and early warning of hazard risks. And the third is service platform for early warning of mining disasters based on technology of network of things, cloud computing and virtual reality. Research objectives of the project is to clarify the disaster mechanism and associated precursory features, to establish the indices for in situ monitoring and early warning. The second part of this presentation is rock mechanics study for early warning of mine disasters. This slide shows the rock failure mechanism associated with mining-induced rockfall. As for the rock failure mechanism, we studied three topics. The first one is analytical solution to stability and large deformation of roof. The second one is rock creep failure triggered by dynamic disturbance. This will be presented afterwards by myself. The third is sliding instability of rock block induced by dynamic disturbance. Now I will focus on the second topic. This slide shows the possible mechanism for the dynamic disturbance may trigger mining-induced disasters such as rock bursts. Mine disasters may be induced by dynamic disturbance. As for underground mining, the blasting may affect the stability of existing roadway. It may induce fractures in the surrounding rock, and may trigger rock falling and rock burst. In particular, when rock is under high in situ stress. This may provide theoretical basis for early warning the occurrence time of mine disasters. In this slide, the first picture shows an apparatus used to the rock creep damage disturbed by dynamic disturbance. The apparatus consists of three key components: creep loading component, dynamic disturbance component, and data acquisition and recording component. Then we did multi-state creep experiments of rock. Prior to performing creep experiments, quasi-static tests at a strain rate of 1 × 10⁻⁵ per second were conducted to obtain the stress-strain curves of the sandstone, as shown in the second figure above. A representative stress-strain curve is shown at the left figure. Stress waves generated by the hammer falling from heights of 300, 400 and 500 mm are shown at the right figure, where the peak stress and the loading rate are indicated. This picture shows a different stress level that rock is under creep state. Then the dynamic disturbance is applied every 12 hours with dropping hammer. This is the waveform of dynamic disturbance. Strain jumps occurs after 2 impacts, then followed by stable creep, which is comparable with in situ observation. The accelerating creep occurs in 1.4 hours after the third impact. This slide shows the numerical simulation of creep impact experiment. In this section, two-stage damage model was established. Constitutive law of steady creep is shown at the left. Then the damage model is used for the numerical simulation. It is found that more damage occurs with the increase of time and stress levels. The fracture pattern is similar to experimental observation, thus validating the numerical model. In this slide, the first picture shows the biaxial impact disturbance experimental device. This apparatus is used to study the mechanism of sliding and instability of key block induced by dynamic disturbance. Diagram of the apparatus is shown in the second figure. For this apparatus, horizontal loading is applied first, and then the dynamic disturbance is applied with falling hammer. This is the incident stress wave excited by the dropping hammer, as shown in the last figure. The basic mechanical parameters of sandstone are shown in the table. In this slide, two displacement modes, Mode I and Mode 2, are found. Mode I indicates that the key block will slide for a distance and return to stable state again. Instead, as for Mode 2, the key block will fall immediately under the disturbance. Also, the experimental results under different clamping loads and impact energies are shown. Under the same clamping load, for the Mode I, the vertical sliding displacement of the key block increased exponentially with the impact energy. The critical impact energy of key block clearly presents a logarithmic growth trend with the increase in lateral clamping load. This slide shows a numerical model is established, and the sliding displacement of key block is obtained by numerical simulation, which is consistent with the measured result. Based on numerical simulation, the influence of friction coefficient and impact energy is also examined. The results shown that, when the impact energy is constant, the disturbed sliding distance of the key block decreases as a power function with the increase of the friction coefficient. When the coefficient decreases, the sliding distance increases sharply with the impact energy. The third part is cloud platform for early warning of mine disasters. In this slide, we propose a new method for predicting or early warning the mine disasters based on combination of in-site monitoring and numerical simulation. As for this method, we collect monitoring data to find the parameter of MS events. Then, we update model according to the MS data and do numerical simulation to predict the response of rock mass. The numerical results are compared to the in-situ monitoring data and to update the numerical model again to predict the future response. We repeat this again and again in order to infinitely approach to reality. The objective of this method is to achieve the numerical simulation based on in-situ monitoring, early warning based on numerical simulation, and prevention and control based on early warning. In this slide, we put forward the technical routine of the cloud platform. It is consisted of 5 modules. The first modulus is laboratory test and theoretical analysis, and the second is insight measurement and monitoring. Based multi-source monitoring, data mining, and numerical simulation prediction. The data integration and data mining is the third modulus. Then the fourth modulus is prediction and real-time early warning, and lastly, the fifth one is risk assessment and alarm information release. This slide shows the hardware architecture of the cloud platform, mainly including monitoring equipment and server. Ongong Information Center, AliCloud and NEU Center for in-situ monitoring and early warning of mine disasters. From the perspective of data flow, the monitoring data collected at the mine is sent to Ongong Mining Information Center, which backs up and cleans the monitoring data and forwards the data to AliCloud. AliCloud backs up all data and forwards it to the NEU Center. The NEU Center uses high-performance private cloud server to analyze these data and integrates the results of large-scale numerical simulation to predict and early warn the mine disasters. Subsequently, AliCloud extracts the prediction and early warning results to the cloud and pushes them to mine. The mine is responsible for the implementation and further decision. This slide shows the software architecture is composed of 4 layers, which are data, service and application and visualization layers from bottom to top. The data layer is used to collect, transmit and store monitoring data and disaster cases. The service layer provides data analysis, numerical simulation, 3D modeling and prediction or early warning. The application layer realizes the visual query of monitoring data, the access of mine virtual scene and the release of disaster information. The visualization layer is to display the data in visual manner. This slide shows the platform includes 5 functions: mine 3D modeling and virtual reality, acquisition and analysis of monitoring data, numerical simulation with 100 million degrees of freedom, fuzzy comprehensive evaluation of disaster risks, disaster information release. The platform can run in PC version and mobile version. This slide shows The first function is to build 3D model and virtual reality scene. With the help of identification of borehole structural plane, statistics of rock discontinuities, the discontinuities can be obtained. On this basis, the 3D geometric/numerical model is constructed. And finally, the virtual reality scene is established with Supermap and Unity 3D. This slide shows. The second is data acquisition and analysis. Multiple protocols are used to receive monitoring data. Then, the MySQL database is used for data management. On this basis, the data is visualized by using Baidu Etchit, and the historical data is analyzed by using clustering, SVM, deep learning and other algorithms. This slide shows. The third is the numerical simulation of 100 million degrees of freedom. In order to improve the accuracy of large-scale computational analysis of rock engineering in open-pit mine fine modeling and parallel calculation are important approaches to achieve it. We have realized the automatic meshing of rock mass into grids with 100 million degree of freedom in order to simulate the mining-induced damage at a mine. The mesh can be imported into numerical simulation software such as FLAC 3D and COMSOL Multiphysics. And the results can be displayed in Supermap/Unity 3D. This slide shows. The fourth is fuzzy comprehensive evaluation of disaster risks. The mixed programming of MATLAB and Java is used to implement the algorithms for rock mass stability evaluation and disaster prediction and early warning. On this basis, the data in the cloud database are analyzed and displayed at the cloud platform. This slide shows. The fifth is disaster prediction and information release. Based on the analysis of historical monitoring data and numerical simulation, the rock damage and failure induced by mining are predicted, and the disaster warning information is released to the relevant users through the platform, email and SMS. Part 4 is Engineering Case Study and Summary. Case Study 1. Slope stability of Dagushan Open-pit Mine. As for the in-situ monitoring, the microseismic monitoring, MS. Surveying robots, 3D laser scanning, inclinometers, GPS surface monitoring, blasting vibration testing were used to collect the in-situ data. About blasting vibration test, it is employed to determine the impact of blasting vibration on the slope and to find the safety distance of blasting. About the borehole camera, it is used to observe the distribution of joints and fissures and water content in the borehole. About the microseismic monitoring, 8 sensors are installed in order to track the damage process of rock in the slope. Since June 15, 2017, 5 staff include Yang Tianhong, Yuqinglei, Lu Honglei, Zhang Penghai, Zhang Yabing and 13 graduate students have participated in the field work. Personnel impetus about 221 people. Days. This slide shows the numerical simulation of 100 million degrees of freedom. The hexahedral mesh of Dagushan Open-pit is constructed. With a total number of 33,163,200 elements, and 100,495,647, over 100 million, degrees of freedom. The potential landslide location is predicted, which provided suggestion for selecting the monitoring location and for clarifying mechanism of slope stability under multiple factors. This slide shows the prediction or early warning of slope instability. The early warning indices of slope instability consists of safety coefficient, deformation velocity, tangential angle of deformation curve, crack propagation, and microseismic events. They are divided into 4 levels, which are blue, yellow, orange or red. Based on engineering analogy to the existing slope instability cases, on May 22, 2018, the slope deformation speed was greater than 10 mm per day. The tangent angle of deformation curve was greater than 80 degrees. The safety factor was less than 0.95. And the dislocation on both sides of the crack on the upper edge of the landslide body, it was 5 days before. A red warning of landslide was issued, and the area nearly 150 square meters was closed. This landslide was triggered by rainfall. Case Study 2. Stability of cavity at Gongchangling Open-pit Mine. The right figure is the top view around the cavity. We installed sensors of microseismic monitoring, rock bolt dynamometer, and multi-point displacement meter in the roof of a cavity and hydraulic level gauge at the surface. In this respect, the damage of roof can be retrieved by MS monitoring before the variation of deformation and stress are measured. It covers the range of 800 meters by 600 meters by 200 meters, with a grid size of 1.35 meters. It is predicted that the cavity is stable through the change of the maximum principal stress and the minimum principal stress of the roof before and after mining. The tensile stress in the roof can be analyzed. The greater the change of the maximum principal stress and the minimum principal stress, the more obvious the roof tension, the more dangerous the roof. The maximum principal stress and minimum principal strain diagram before and after mining are shown in the following figure on the right. This slide shows, based on the historical data from other similar engineering cases, the stability of GOF was evaluated, and the surface deformation was also predicted. It is evaluated that the cavity is in low risk of failure. It is stable during mining operation. Summary. Rock mechanics study for early warning of mining-induced disasters is introduced. Idea for early warning based on in-situ monitoring and numerical simulation is proposed and implemented. The cloud platform for early warning of metal mine disasters is built, and it is used for stability evaluation of rock slope and GOF at metal mines. 2 engineering case studies are given. Thank you for your attentions. I am looking forward to your comments and suggestions.